What's up, everybody? Let's get started here. Let's do a little bit. Oh, who's watching? Who's here live? Who is here? Say hey in the chat if you're here. I think I got a little burned outside day. It's warm out. It's a very nice day. Dee, good to see you. We're going to do, look at this. I got some sun. I can't feel it yet. I'll feel it when I get home. It's bright out today. With that, we are going to do a little bit of the chapter 12 or 13. Chapter 13, data analytics. What am I saying? Don't listen to me. Don't listen to me. I feel like I'm YouTube addicted. I am too. I am YouTube addicted. Streaming on YouTube doing... No! Let me throw you some points. You get the big points. Let's throw you 100,000 points. I've been doing 100,000 points in class. I'm always glad to see someone here. I'm always glad to see you here. Not just somebody. I don't want to say... I am glad to see you. I'm glad to see my students. I am, when you stream online, you want people to be there. As I'm going to do some assignments. And I think there's just been a change to the system with like ChatGPT. And everyone watching this can hear this if you watch this first part of the video. All these things. Well, thank you. Is we're talking about how to like reorganize the class because with ChatGPT and everything, we fear a lot of people aren't actually, there's been a lot of conversations and a lot of like, how do we help people learn? Because a lot of times people go to the quickest path to things. They're like, well, it's 11 p.m. at night. I can learn this, or I can just put it into ChatGPT. And, I'd be tempted too. I'd be like, I can just get some answers pretty quickly to these questions. But the goal is that we understand how to do them. And then as we build knowledge in other areas, it builds on top of it. And the problem is the less knowledge you have building, you get to a point where the house of cards crumbles. So our goal is to try to restructure in some ways to help create and facilitate better learning, which goes to pedagogical changes. So then these are the conversations we're having. And it's tough because we as educators are going through this. So here we'll do the first one. This is Stat 201 chapter. Didi, you just said it right there. That's a change we're doing for the upcoming semester. It's a lot of more in-person, some shifting of weights, probably doing those things right there. So you want to teach? Because that's what we're doing. But yeah, homework question 1. Here we go. Chapter 13, homework, and reorganize that a ton a bit. Okay, so this first part is actually talking about how to interpret confidence intervals. So it says a Pew Research did a poll in 2018 and polled 1,058 random, there it is, U.S. teens, and asked them about their internet usage. 45% said they were online several times a day. A fact, I like the points right there, a fact that interest advertisers, 95% confidence intervals gives the 42 to 48%. Now, here's the cool thing, as Didi checked out the points right there, is if you go to confidence, and you'll see this in the chat right here, MuBot's actually going to give the interpretation of a confidence interval. So he has that write it down symbol next to it. We're going to bring it over here. And there it is. I am blank % confident that the true blank is contained in the interval blank to blank. So you want to be able to do this right here. And I'm going to disappear so you can see it. Well, first off, when you do the % confident, you literally just take what the % confident is and drop that in there. So where it says I am a certain % confident, well, that would just be I am. I'm going to try and make this bigger, but I want to keep everything on the screen. Well, you know what? If I do this,
wow.
Now it's on the screen at the same time. I am 95% confident, which is your degree of confidence, that the true, and this would be proportion of teens who are online constantly, online several times a day, the true, and this would be a proportion, because it's like a percentage, you could say percent, that wouldn't be bad, is contained in the interval 42 to 48. And look at that. It's not too hard to write this. You can see the information down below. But you say how confident you are, and you can say the percent right there. I am 95% confident that the true proportion of teens that are online all the time, it says something like that, online several times a day. Here's some criticisms from my side, but I've been waiting to tell my professors, but I've never had the courage. AI, I feel bad when my course materials. Yeah, I do too. Thank you, Didi, for sharing that. A lot of our students report that they don't like AI generated course material, and we try to stay away from that. And I don't use a lot of it. You won't see a lot of it here. MuBot is commissioned artwork. Ain't that right, MuBot? We've had MuBot for a long time. Before AI, he is all ours. That's right, Skeletor. Yeah, that's a GIF I took from the internet. Yeah, what's the point of coming to class if people are, it's just all AI? Yep, no, I agree. That's why we're here to help teach these things. I am 95% confident that the true proportion of teens who are online all the time is contained in the interval of 42 to 48%. And so now we go down here, and is this the correct interpretation? Well, one is sounds a lot like I am 95% confident that if we were to ask all the teens, then this is the proportion that would say it. So if you look at the way this is worded, I am 95% confident that the true proportion of teens who are online all day is contained in the interval 42 to 48%. Pretty close. AI generated programs or even art is fine. Exactly. I am partial towards those things, but you have to put some effort in. I have done some different versions of MuBot that are AI generated, AI updated. But the original MuBot is a commissioned artwork that I have the rights to. Yay! Explain what this means, 95% confident. Well, 95% confident doesn't mean for one interval. And there's actually, check this out, Didi, you're going to love this. There's a website called Seeing Theory. And hopefully they still have the page up, because one time I went to it and it was like, this page is no longer existing. So here's the page for Seeing Theory. And we want to go to confidence intervals. Yes, the page still works. So this is what a 95% confidence interval means. It means, and let's go to normal here. It means when you build 95%, and we'll put this to 95%. Oh, it's going to be so hard to get it right there. What did they do a slider? 95%. So there's a 95% confidence interval. If you were to start making intervals, then notice this is the truth, which is mu. Yeah, I'm a frequentist. You bet I'm a frequentist. No information theory here. No Bayesian. Notice 100% of the intervals so far have contained the truth because, that one didn't. So 1 out of 24 didn't contain the truth. So this is simulating sampling 5 observations, creating an interval from the 5 with a center, which is the dot, and then the expansion, which is the lower to the upper. We talked about intervals in class. So Russell's chicken. I don't know what that is. And then that interval barely did not contain the truth. But this gets to the law of large numbers that if I keep letting this simulation here run, 95% of the time it'll contain the truth. Now I know we're exactly at 95% right now, but I wish it would show also, shouldn't have gone off screen. If you have to let it run for a very long time. We've ran decently long enough, but in the long run, 95% of 95% confidence intervals contain the truth. So why am I saying this to you? A 95% confidence interval, read Nate Silver. I know Nate Silver really well. Well, I don't know him, but I know he's big in stats. He's 538 Nate Silver. But a 95% confidence interval means 95% of these intervals are expected to contain the truth 95% of the time. So it's not about one interval, because one interval does or does not contain the truth. It's 95% of intervals created. If one created many random samples, about 95% of those intervals constructed would contain the true proportion. And I misread, is it of size this? I totally missed the of the size, because they're going to be like, well, of the size, sorry, I was reading too quickly. 95% of 95% of confidence intervals created from a sample size of 1,580. Not as important, but 95% of 95% confidence intervals contain the truth. So if you keep running this simulation, as you can see over there, and keep making intervals, 5% are expected to not contain the truth. 95% are expected to. Well, yeah, I need to check it out then. I need to check that out, Didi. So seeing theory is really awesome. I'll probably use it in class some. That's the first question. It's just theory about making intervals. I am blank percent confident that the true blank is contained in the interval blank to blank. And then also 95% of 95% confidence intervals are expected to contain the truth 95% of the time. 90% of 90% confidence intervals are expected to contain the truth. And you can just do this. You could do the same seeing theory and go over here and just do a 90% confidence interval. Just go here and it's already set to 90. And they start running the sampling. Was it not sampling? I don't know. Oh, it's all on one page? I didn't even know that. Well, now, I didn't select distribution. So you can run this, and 90% of these intervals are expected to contain the truth. And this would be seen in the long run. So you would have to keep doing this. Now it's at 100%, but if you keep running it, eventually it'll get closer to 90% due to the law of large numbers, which says we will see the true probability of an event in the long run for the long distribution of trials. Okay, reaching out to standard errors makes a what percent confidence interval. And here's the thing. You don't know these answers unless you can get it without clicking. I like I'm gonna look at Didi's answer / question here in a moment. Now, why do I say you don't know these if you click on it? Because it gives you hints. So here it is. Here's how to get it. Well, so what numbers did I just say? I just said the empirical rule numbers. So if you know the empirical rule is the classic. We're going to put it here to a new page, but it is the classic 68, 95, 99.7. So 68 is 1, 95 is 2, 99.7 is 3. But here's the issue we run into is when you're doing these intervals, you don't always use a 95%. 95%, 68, 95. And here's the thing, 95 isn't exactly 2. 95 is actually 1.96. So if you go to the between right here and do 95% between, it's 1.96. But it's not even 1.96, it's 1.95996. There it is, 1.9. Oh, got to do another decimal, 1.95996. So what's the next decimals? I don't know the next ones. I didn't memorize that far. Most statisticians just say 1.96, but if you're Brian, you're going to say 1.95996. And you can find any interval you want right here, like a 90% is 1.645. There's a 5 after that. Or 98% is 2.33 or 2.3263. And 99, look, if you go out a little bit more, it's 2.5758, which will round up to 2.58. I tried to memorize all of these to 4 decimals, and I know a lot of different ones. I think this one is 1.2816. There it is. And this one, I don't know the next. Oh, no, I know this one. It's 0.6745. There we go. You don't need to memorize these. But as you get more confident, the interval gets wider. And look, right here when we reach 68, it reaches about 1. 68 is 1 standard deviation. Go to 95, and you get to 2 standard deviations, basically. This is the exact z-score. And then 99 and then 99.7 would be 3, but the fun last number on that is 99.73. So that's the actual one. We usually teach you just the basics of 68, 95, 99.7, but going out 2 standard deviations gets you to a 95% confidence interval. And let me look at the question here. He gives the probability of winning if you go all in every poker match and the win rate is 92%, but the expected win is negative 3. Oh, I could see that. And I need to look at that. That's really cool right there. Is that like playing chicken with poker? Like you just go all in and I know it means going all in, and it'd be a horrible decision because if you keep going all in, you'll probably win a lot of the antes, which are the smaller bets. But then if you have whatever you have, you're going all in on, and people are gonna be like, well, they just go all in every bet. So I'm just gonna wait till I get like kings or aces, or I'd even go in with someone with like 10 jack suited. If I saw someone go in repeatedly like 10 times in a row and it was just heads up, me versus them, and I had 10 jack suited, I'd go in. High suited, that'd be good. Versus a random. Let me see. I'm gonna find out. Ranking all poker hands heads up. What is the percentile of 10 jack suited? Okay, so I would guess it's like the 15th or 20th percentile. So I would guess that. Let me put the next question in here. So I'm going to find out the percentile. Like I would guess I'd have like, versus a random hand, I'd have like an 85% odds probability of winning. So I'd be like 10 jack suited. Psh, I wouldn't go all in on that normally, but if I saw them go in 10 times in a row. One time I was playing poker and this guy and I went heads up all in, and I think I beat him with like 8-9 offsuit, and he had pocket queens. And then the next hand, I think he had pocket jacks. He went all in. I had pocket kings, and he was so mad. He was on tilt. He was like, "You do not actually have pocket kings." And I was like, "Yes, I do. Pocket kings." It's like, that can't be real. It's doing the math over there. I'm trusting ChatGPT on this one. A morning consult poll polled 1,997 voters, almost looks like a year. And they found out the people who said the country's going in the right direction was this, and the wrong direction was 75.1. Oh, the wrong direction was 24.9. The right direction is 75.1. Now we have to figure out the margin of error. So for these questions right here, it really boils down to
notation, brother.
So the margin of error, he's got some good comments. I like it. The margin of error is going to be everything after the plus or minus. In this interval, it's going to be, we'll put over here p hat, which is the estimate. And then the margin of error is this, and that's going to be z times p hat q hat over n square root. And so we have estimate and the margin of error. Now p hat, we want to figure out the proportion saying we're going in the wrong direction. So the wrong direction was this, and that makes this p hat. And then q hat, that's not my color that I wanted. Q hat is 1 minus, which is this, and sample size n is going to be that. And then the z-score is related to how confident we are. And it says making 95, and we just learned that 95 is 1.96. So z equals 1.96. Now, if you don't know how to get your z-score, if it says something different like 90%, you need to go to the apps on the screen. You're all right, Didi. I'll read it in 1 second here. You need to go to the apps on the screen. I just put the apps in the chat again. I'll have to click it. But if you go to the apps right here to get the correct z-score, you need to shade the middle portion of the curve, and you see how that's 1.96. If you have something like 90, you can just type in 90, or if you have 80, or if you have 98, these are the z-scores to use. I do suggest using 4 decimals. Mine with 4 decimals is 1.96. It's a very classic statistical number that all statisticians probably know, I would think. Ask a statistician, what is the z-score for a 95% confidence roll? And they should say 1.96. Or they'll say, I haven't been in school for a long time. They'll say, I don't remember that. I'll be like, no, it's the most classic of z-scores. So all we do now is just plug in the numbers. This problem has become a plug in the numbers problem. So 1.96 square root point, and we're going to put this one here, 249 times 0.751 over 1997. There we go. And we're just going to solve the problem. So 0.294 times 0.751 divided by 1997. And now we square root. This is called the standard error. So that portion up there that I'm hovering over, this is the standard error. And then by timesing it by 1.96, we turn it into the, I did square root it, good. We turn that into the margin of error. So it's about 2%, not quite. But we bring down to 3 decimals, and we should get it right as long as we didn't do a math error. That's got it. That's got it. And last question right here for this one. Explain what the margin of error means. It means about how far we are away from the truth. Like, here's my estimate, but I could be off by about this much. Like, the truth might be contained about this far away. One is 95% confident that the observed proportion of delts on the wrong track is within this of the truth. So we're trying to figure out where the truth might be, and we're 95% confident that the truth would be within this far, not that far from our estimate of the truth. Didi says, Russell's chicken is something different. It's a critique of frequentism. Ooh, essentially, if a chicken wakes up every day and sees that it gets fed every day, it can expect to be fed for the next day. But one day it wakes up and sees its meat. No, that's really, actually, I need to look into that. That's a pretty interesting. Well, but was the chicken not justified? Is the frequentist not? So that's interesting. I wonder who Russell is. He also the guy with the teapot? I know of a Russell's teapot. It could be. Russell might have a teapot and a chicken, and drinking his tea as it orbits Pluto. And so Russell might. Is Russell the teapot and the chicken guy? Is he critiquing multiple things? Could be. Could be. We need to find that out. But no, is the chicken not justified to think it'll get fed? One day it becomes the feed, but I see what you're saying, because the frequentist estimates the probability of an event by looking at the frequency of the occurrence to estimate the true probability of an event. And the chicken's like, well, I always get fed, so I'm always going to get fed because I've always been fed. So every day I get fed, so I will get fed because the probability is equal to 100%. But, same guy for the teapot? Man, Russell's doing a lot. Is he still around? If he is, I'd like to meet this Russell guy. He's done some interesting... He's a good teacher. Talking about teapots and chickens. So he was a philosopher and frequentist dude? Or like critique of frequentism? Is he a Bayesianist? Bayesian? 1970? Well, what's interesting is he would have been around when Ronald Fisher was around. Ronald Fisher passed in the 40s? So he might have been a contemporary to Ronald Fisher. He'd have been a contemporary to John Tukey. If you look up John Tukey, very interesting, worked at Bell Laboratories, the inventor of the term software and bit. So John Tukey, Ronald Fisher, William Gossett. He's too young for... he might have known William, a little young for William Gossett. William Seeley Gossett. Let me retimestamp this real quick. I love this kind of stuff. Thank you for telling me that, DD. I didn't know Russell's chicken. Now I'm going to talk about the chicken and the teapot. Good stuff. Now we have to make it 95% confidential. How are we going to do that? Well, it all boils down to
Notation,
brother. All about that notation. Yeah, I know. It's Tukey. Look up John Tukey. And then also, who's the guy I'm thinking of? I'm thinking of, my dad has a book signed by him. Well, I have a book signed by him now. My dad gave it to me. My dad's still around, but All Models Are Wrong, Some Are Useful, George Box. George Box sadly passed away around the year 2000, but George Box did a bunch of interesting work too, like in process. George Box probably. Okay, so the equation is p hat plus or minus z star square root p hat q hat over n. So the important thing is knowing that is correct, or almost exactly. And Didi's pointing out some great stuff right here because Didi's already starting to solve this. The p hat is the sample proportion, so it has to come from a sample of size n. So whenever you see p hat, it comes from a sample. And then when you make a 95% confidence interval, it's almost 2, but it's more exactly 1.96. Or if you're Brian, it's 1.95996. And this is the z-score. So if you're looking to get z-scores, there's a bunch of z-tables and everything. Don't use that one. Use the one I highlighted. So if you're working this problem right now and you can't find the z-score, and you might wonder why I say this 3 times, it's just because someone might be watching this problem who didn't see the previous one. You need to go to the apps on the screen that MuBot is so politely putting there. Would you kindly put the apps on the screen, MuBot? Would you kindly? He did. Thank you. And between and select 95 or whatever your interval is, and you will get the z-score. I do suggest using 4 decimals for this. So use 4 decimals, and you will still see that when you do the z-score to 4 decimals for 95, it is 1.96. If you go further, you do see the 1.95996, but that is not required. And so now we just have to find q. We should know that q hat equals 1 minus p hat. So all we do is just do 1 minus 0.523 equals 0.477. And that is going to be the q hat right there. And guess what? We have now written our equation for solving this. This is going to give us the lower and the upper bound to put into that equation there. So all we need to do is solve it. When I solve this, I like to solve out the margin of error. This is made up of the z-score and the standard error. So the standard error is this component there, and the z-score gives us percent confidence, hence why it has a star on it. So we're just going to plug in the numbers. Let me do that right here. Okay. So we plug in 0.523, 1.96, 0.523, 0.477, and we plug in, it's 2019 study, but 4,527. And so now let's go through and start solving. So we do 0.523 times 0.477 divided by 4,527 and square root, and then times by 1.96. And that is the margin of error. Very important to know that. So it's 0.0145. Plus or minus 0.0145. And then the center of the interval is 0.523, which is 52.3, plus or minus. And then 1.45. There we go. And so all you do now is just add and subtract that 1.45 on that. So that's going to be about 50.85 and then 53.75. Basic question. Well, I got this a moment here. Let's take a look. So you just add and subtract 52.3 minus 1.45. And then just, I can't put it there. And then just add. So we can add that 0.145. 0.145 added. There's the added. That should do it. Round to 1 decimal. Come on, no. Okay, I'm a little worried. It says round to 1 decimal. Woo! Basic question. Why do we use the normal? I always learned most things follow that distribution, but where do you get this idea from? Why does it naturally align with the normal distribution so well? That's such a good question. Here, I'll answer it right after this one. You got it. You remember that interpretation we had Mubot write out? I am 95% confident. We use this interpretation right here of the I am this percent confident. So one is this percent confident that the true proportion of Californians who plan to move out of state is contained in the interval this to this. And so DD actually brings up a really good point right here. Why do we use, well, wait, there's one more. Since the interval is greater than 50%, that would be evidence that more than 50% plan to move out. So they should invest because they're going to invest if more than 50% plan to move out. So they're asking, is there evidence of that? Yeah. Can you show me the page as well to show the work for this? Oh, yeah, I'll show the page with work right here. Here's the page with work. So the reason we use the normal is because of the central limit theorem. So the central limit theorem basically states that the distribution, and this is a theory that's been around for a long time. I don't know if you don't know. Yeah. It's the whole thing. It might be a little premise not true, but yeah. So here is how the central limit theorem works. And we're dealing with two types of data right now. We're dealing with quantitative data and categorical data. This is showing the central limit theorem. That's according to the thing. It's like 51 to 53%. According to the question, it's saying that, but it's like they just made up data, which bothers me about their questions. But imagine, DD, if we had data that looked like this right here. Is that normal looking data? Can we do the 68, 95, 99.7 on this? Should we talk about 68% of observations are contained between here? Well, what we often do in statistics is we don't work with the data itself, known as the parent population. So this is like, imagine this is people's slices of pizza they eat. You've got like bimodal distribution. You've got people eating like no pizza and people eating a lot of pizza. You could even do this right here. You could make a distribution totally devoid in the center of it. And what's really interesting when you think about this, what's going to happen? So this is a very bimodal, sharp distribution. What's going to happen if you got 5 random people? That was actually a really weird distribution of 5 because we only got 1 from one side. And there we got only 1 from that side. So 5 random people is what we're actually looking at because we're looking at the distribution of means of sample size 5 when we do t-tests, which are on the mean. So the t-test is not on the distribution of the original data. It's on what we believe the distribution of the mean is. So down here below is the distribution of the mean of sample size 5. That's not normal either. But guess what happens as we start to take larger samples? If you were to take 10 observations and find the mean and do this repeatedly, you would see what the distribution of the mean of sample size 10 looks like. So you can see right here, it looks different than the previous one. And what do you notice is happening? As we take larger samples right here, you're going to see that the distribution keeps becoming more and more normal and also tighter. You'll see, well, now it's normal. Now the distribution is tighter by a factor of the square root of n. As in, I could take this original standard deviation of 13.34, and this is all being done via simulation, so it's just real data, like real simulated data. And I go square root of 20, and I can tell you what 13.34 divided by the square root of 20 is. Well, it's going to be about 2.98. There it is. That's because this new standard deviation down here is the original standard deviation divided by the square root of n. And you can see that in my math. This is 13.34 divided by the square root of n, and that's the original standard deviation right there. So this is the distributions of means of sample size 20, which when you have a large enough sample size will be approximately normal and have a standard deviation that is tighter by a factor of square root of n, but the mean of 20.43, notice how it says 20.43, watch this. It's not going to say 20.43 for long because I did more simulation. So the answer is, a lot of data is not normal, but because of the central limit theorem, the distribution of the things like the distribution of the mean, of sample size, whatever we're doing in our problem, will be approximately normal given we meet certain conditions like the large enough n condition. And there's other distributions too, like the binomial distribution. So the binomial distribution is what we're actually working with quantitative data. And so here is the binomial. Forbidden. Wait, what? That's weird. Iowa. Why did that do that? Please work. Oh, that's weird. Wait, can I make a binomial? Okay, wait, you ready? For some reason, his website's not working. I hope it's not been hacked. Make an applet for me that simulates a binomial distribution in R, where I can select the true proportion and the sample size. Make this a cool, amazing, shiny app that is beautiful. So I love using, we're going to show this on the screen, then it'll be end of office hours. But I love showing how we can use ChatGPT and stuff to do coding very easily. It's really made my life a lot easier, and sadly has probably made me worse at code. I'll just admit that. But you can get so many codes. Oh, man. And the comment is roughly... Wait, what? In the common 169 starting hand rankings, it ranks... Oh, well, it's saying it's in the 91st percentile. 10 jack suited is top 9% of hands. Yeah. So it's saying 10 jack suited is really good. So I can't see. Oh, yeah, I'm back. The question we asked earlier about 10 jack suited is very high up there, apparently. King jack suited is very good, too. Yeah. Bottom 50% is 7-2, obviously 8-3 offsuit. So, yeah, you'd probably be better with 10 jack suited against fives. Would you? I don't know. Oh, thank you. Appreciate that. Why is it zipping it up? Oh, it's creating an R file for me? I just want you to write a code, ChatGPT. Why you take so long? You used to just give me code so fast. It was so quick and easy. It was so quick and easy. Now it takes forever. I'm going to hit answer now. Still pausing. Love this. This is perfectly aligned with your teaching style. Thanks. Here we go. Getting code finally. Okay. Almost there. Yeah, I'll check it out later. It'll be good reading. Okay. I don't know what it was doing. It was like just thinking. It was like, oh, I got this. Okay. It's quicker than I can write all the code. I'll tell you that much. Okay, there it is. Hopefully I have all the packages. Looks like I do. Why are things being weird? Resimulate. Does it not work? No. Oh, 2,000 simulations? That might be why. Well, ChatGPT, you couldn't download the Google font. Wait, what? Where did it do that? Google font. Font base, font Google. Maybe that's why. Well, it won't simulate. Let's try one last thing. I got one more minute. Also for QFire, I don't see how the results follows. There's the reason if you want. Yeah, no, it's just like if more than 50% want to move out of state, we're supposed to like do some sort of plan. The whole thing is to see if you see that the interval is completely above 50. So we would think 50 is not a reasonable value. We would think we could reject 50. This didn't work. Redo it and make it work and better. Okay, so here we go. Last try on here. That didn't work. Answer now. I think it's incorrectly teaching students. Yeah, and that's a big thing is we're talking about like we want to write more of our own questions. No, I agree. There's a lot of questions I like, and then there's some I kind of like, and then there's some I'm not a huge fan of. And I don't like fake data questions, and there's a lot of fake data questions. Oh, there it is. Look at this. A little weird on how it looks. But if I set the true proportion to very low, there we go. That's what I wanted to see. And if you look, that is going to be skewed to the right. And if you were to, I'm trying to make it smaller. If you bring it more towards the center, it'll actually be more normal due to the success failure, and now it'll be skewed to the left due to that. But actually, if you raise up the sample size right here, it's not going to have enough successes, but it'll actually become more normal. Like if we were to do this, you can see this is, that's approximately normal. But then if you bring down the sample size, you're going to get a skewed distribution, especially with that. So now you've got a bit of a skewed distribution because you lack enough successes and failures. So that can't be modeled with the normal. But once you reach at least 10 successes, at least 10 failures, you can use the normal. Yeah, Claude's amazing. Well, that's got it. I have to run. I've got class coming up. Dee Dee, thank you so much. Class coming up in 4 minutes. Bye for now. Bye.